Hi, everyone. Today I wanted to walk through one of the papers that I helped publish while I was an undergraduate student at university. Now, papers can be incredibly overwhelming and technical, so I thought it would be helpful if I walk you through this paper and I take you through the title, the introduction, the methodology, the results section, and our conclusions so that you don't have to have all the background knowledge in order to understand some of the really cool research that we did. And so that's what we're going to do. And I'm going to start right here at the title. Now, bear with me. I don't have this title memorized. I'm going to have to read it from my notes. So this paper is called Exploring Structure Property Relationships in a Family of Ferrocene-Containing Triphenylamine-Based Hybrid Organic Dyes. Oh my, that is wordy and technical. And some of you may be like, oh my gosh, no, just no. And so I am going to break down what that title means and the background knowledge that you need in order to understand that title. And so let's start here. On the screen, I have a molecule. This molecule is the focus of the paper. This molecule was actually patented by my professor. So this structure is patented. It's pretty cool, right? But let's hone in on the different parts of this molecule. In the title, it said that we are working with a ferrocene-containing triphenylamine-based dye. Let's hone in on the word triphenylamine. Triphenylamine is a molecule that has 3 phenyl groups bonded to a nitrogen atom. In this molecule, we have 2 triphenylamine units. Now, why is this important? Well, this molecule is highly conjugated, which means that it has a whole bunch of alternating single and double bonds, which means it's able to absorb light in the visible region. And that's what gives this molecule its color. And you can see in this picture here that it's got a beautiful, vibrant orange color. And that's actually why we call it a dye. A dye is a colored molecule. And now you're starting to understand where the title of this paper is coming from. But specifically, the title has said that it's a ferrocene-containing triphenylamine-based dye. Ferrocene is a special molecule in itself. It looks like this. Notice the iron atom, and that's the key. Ferrocene contains iron. Iron can be oxidized and reduced. Oxidation is the process of taking an electron away from the iron atom. Reduction is the process of giving that electron back. So ferrocene, because it contains iron, can be readily oxidized and reduced. And you can do this over and over and over and over again, and the ferrocene does not degrade. And that's its key property. And so what we did is we took those ferrocene groups and we bonded them to our molecule. And that gave us a ferrocene-containing triphenylamine-based dye. Now, when we combined the redox properties of ferrocene with the conjugated structure of our triphenylamine-based dye, we realized we had something special because the conjugated structure allows the dye to absorb light in the visible region. And the ferrocene units give this molecule redox properties, so it can be oxidized and reduced over and over and over again. And now this combination is really good for dye-sensitized solar cells. Dye-sensitized solar cells, or DSSCs for short, are able to generate electricity from sunlight. And this is just like your typical solar panels. But your typical solar panels will contain a semiconducting material, like silicon. Sunlight will strike that material, exciting electrons. These excited electrons can be used to generate electricity. Dye-sensitized solar cells are very similar, but they don't contain the same semiconducting material. Instead, they contain dyes. When sunlight strikes those dyes, it excites electrons. These excited electrons are able to move through an external circuit, generating electricity. And that's the key difference. Dye-sensitized solar cells contain dyes, like the molecule we were just looking at. Now, there's other components of a dye-sensitized solar cell. There's the anode, the cathode, the electrolyte. But in this paper, we honed in on the dye, and we wanted to see if we change the structure of our dye, that will change the dye's properties and potentially make the dye more efficient at converting sunlight into electricity when we put it in a dye-sensitized solar cell. And so that's the point of this paper. We wanted to change the structure of our triphenylamine-based dye so that it has different properties. Specifically, we wanted to see if adding that ferrocene group to the triphenylamine-based dye improved its efficiency in dye-sensitized solar cells. And now you should have all the background knowledge you need to understand what's going on in this paper. Isn't it crazy, though, just how much you needed to know in order to understand the title? But I will say that most authors put a lot of that background knowledge in the introduction. Now, looking at our introduction in this paper, I want to hone in on this image here. This image shows the structure of the molecules that we were testing. Now, we had two families of dyes. Notice we had one that only had one triphenylamine unit, and then our second family of dyes had two triphenylamine units. Now, I want to focus in on the R groups on these molecules. This R variable just tells us that we changed the functional groups at that point. And we did a whole variety of functional groups. You can see a few of the structures just had hydrogen atoms, a few of them had bromine atoms, a few of them had ferrocene, and then a few had these alkyl ferrocene units. And so this image shows all the different structures that we explored in this paper. Now, how did we make all of these different molecules? Well, we used a variety of organic synthesis techniques. And so now we're going to look at the method section of this paper. This is where we broke down all the different steps that we used in order to synthesize these molecules. And now let's just look at one of our syntheses here. I want to break down all the different reagents, solvents, conditions, and catalysts that we used in order to make these molecules. Now, looking at this synthesis, you can see we started with our triphenylamine-based molecule. And what we wanted to do was a bromination. A bromination is a great example of an electrophilic aromatic substitution. So what we wanted to do was replace the hydrogen atoms at the para position with bromine atoms. And we did this using NBS. So that's our reagent at the top of the arrow. But what are all those things at the bottom of the arrow? Well, THF and ethyl acetate were our solvents, and we use them in a 1-to-1 ratio. Then underneath that, we have 94%. That tells you that we got 94% yield for this reaction. And by the way, that's a fantastic yield. I had some reactions where I got like 10%. So 94% was awesome, but brominations usually go pretty well. Now, the reason we needed to do this bromination is because we wanted to do a Suzuki cross coupling. This is a really important reaction because we're going to form a carbon-carbon bond. The way we do this is we take our ferrocene boronic acid and we react it with our brominated triphenylamine. And what we're going to do is we're going to replace the bromines and the boronic acid with a carbon-carbon bond, connecting our ferrocene unit to our triphenylamine. Now, a really important thing that I want to point out for this reaction is that we used a catalyst, specifically a palladium catalyst, PDDPPF-Cl2. This catalyst is critical for this reaction. It will not work without it. And so if you want to Google Suzuki cross-coupling reactions, you'll learn why we need the catalyst, but I'm not going to get into that. Just know that it was super important to use this very expensive palladium catalyst. Now, the last step of this synthesis was to convert the aldehyde groups here to cyanoacetic acid groups using a Noble-Nagel condensation reaction. This is a super important step because you can imagine those cyanoacetic acid groups are like anchors. They connect the dye to the anode when we're making dye-sensitized solar cells. Now, that is just one of the many different syntheses that we did in order to make all of the different molecules that we explored in this paper. Now, I want to move on to our results. And so our results section is split up into a few different parts. We're going to start by looking at the first part, which is where we explored the optical properties of the dyes. So we were exploring how the dyes responded to light. When we were exploring the optical properties of the dyes, we really wanted to know what wavelengths of light do these dyes absorb, and what happens when you shine light on these dyes. Now let's start with the first question. What wavelengths of light do these dyes absorb? In order to answer that question, we need to do UV VIS absorption spectroscopy. So how do we do that? Well, we make a solution that contains our dye. And then we take that solution, we put it in a cuvette, and we put that cuvette in a UV VIS spectrometer. Now, what this spectrometer does is it takes all of the wavelengths of light in the visible spectrum and shines it at your solution. And it has a little detector behind your solution that measures which wavelengths of light were able to make it through, and subsequently, which wavelengths of light were absorbed. And we can see what wavelengths of light were absorbed by looking at the absorption spectra. The peaks on that spectra represent the wavelengths of light that got absorbed. Now, looking at the dyes that we explored in this paper, we can see that they absorbed most strongly around 350 nanometers. Now, that's in about the blue region of the visible spectrum. So we say that these absorptions are blue shifted. That would mean they're absorbing low wavelength light. And now I want to point out something about colored molecules. The color that a molecule appears is not the color that it absorbs. If it's absorbing that wavelength of light, then that light is not hitting your eye. So we're not going to see a blue molecule if it's absorbing blue light. We are actually going to see the complementary color to the color that's being absorbed. So in our case, if we're absorbing blue light, the complementary color to blue is orange. And that is why these molecules appear orange. I thought that was super cool. But anyways, so now that we understand that, the next question is, what was happening to the electrons in those dye molecules when we were shining different wavelengths of light on them? In order to figure that out, we actually did a really cool calculation. This calculation, and bear with me, it's got a long name, so I'm going to have to read it in my notes. It's called time-dependent density functional theory. These calculations help us determine what happens to the electron density as we're shining light on these molecules. Before we go into that, you have to understand what's happening when you shine light on a molecule. We're shining light onto these dyes, and we're exciting electrons from the HOMO. HOMO stands for highest occupied molecular orbital. You can think of that as the ground state. We're shining light on those electrons. That light provides energy to the electrons. It excites them up to the LUMO, the lowest unoccupied molecular orbital. Now, it takes energy in order to go from the HOMO to the LUMO. That amount of energy depends on that HOMO-LUMO gap. If it's really big, it's going to take more energy to excite those electrons up. If it's really small, it's going to take less energy to excite those electrons up. Conjugated molecules have a smaller HOMO-LUMO gap. That is why they can absorb light in the visible region, because that's pretty low energy light, but it's got enough energy to go from HOMO to LUMO in these highly conjugated molecules. But backing up a little bit, when we're exciting electrons from the HOMO to the LUMO, we are changing where those electrons are in the molecule. We're changing the electron density. We're moving it. And so we want to visualize where that electron density is moving to when we're shining light on these molecules. How do we do that? Well, we use time-dependent density functional theory. And we do this calculation in order to visualize that electron density. So let's take a look at this diagram here. What I want you to notice is that when the electrons are in the HOMO, so they're in their ground state, we haven't shined light on them yet, the electron density resides around those R groups. So it's not at the anchors. That's a good thing, because what we want to happen in the dye sensitized solar cell is we want to shine light on the molecule and have the electrons move from the R groups over to the anchors so that they can then go into the anode and go through the electrical circuit. And notice, when we shine light on those molecules, exciting the electrons from the HOMO to the LUMO, the electron density shifts towards the cyanoacetic acid. That is ideal. That means the electron density is being pushed towards the anode, which is where we want it. So these time-dependent density functional theory calculations are really insightful for seeing if your molecule can be used in a dye-sensitized solar cell. But now we're going to explore the electrochemical side. What I mean by electrochemical properties is the molecule's ability to be oxidized and reduced. This is a critical function of molecules that are going to be in dye-sensitized solar cells. Because when a dye is in a DSSC, we are going to shine light on it, exciting electrons, oxidizing it. Those electrons are going to travel around the circuit. They're going to then be returned to the dye, reducing it. So this dye needs to be able to be oxidized and reduced over and over and over and over again without degrading. And that's what we wanted to test. But how do we test that? Well, we use a technique called cyclic voltammetry. Cyclic voltammetry was one of my favorite techniques that I did for this paper. Now, how do we do a cyclic voltammetry experiment? Well, first you make a solution containing your dye. There's a few other things you put in there, but you can imagine your dye is in a solution. And we're going to put an anode and a cathode in that solution. And we're going to run a potential between them. That potential is going to make it so we can oxidize the dye. So we're removing an electron from it. That electron will then create an electrical current between the anode and the cathode, and we can measure that. And then we're going to switch the potential, and we're going to return that electron to the dye, reducing it. And again, we can measure the current as we do that. And that produces a cyclic voltammogram, which you see here. Now let's take a minute here. You can see on the x-axis, we have potential. On the y-axis, we have current. And you can see all these different peaks. What do they mean? Well, looking at the first peak on the left here, that would have been the first oxidation, so the first electron that would be removed from the dye. And that creates a current. That's what the peak shows. But then we keep increasing the potential, and we actually oxidize the dye again. So we have a second electron being removed from the dye. That's the second peak. And then if we keep increasing the potential again, we can remove another electron from the dye. And that's where the third peak is. But then at a certain point, we switch the potential. And now we're going to be reducing the dye. So we are returning the electrons to the dye. And that's where the other peaks on the bottom come from. And now ideally, when you're doing cyclic voltammetry, the oxidative wave at the top and the reductive wave at the bottom are symmetrical, because that would mean that your molecule is being oxidized and reduced without degrading. And the molecules we tested were actually pretty good. Our cyclic voltammograms look decent. If you Google some, you'll see some really ugly looking cyclic voltammograms, and I thought these looked pretty nice. And this wasn't surprising. The molecule we were working with, the triphenylamine-based dye, we've tested before using cyclic voltammetry, and we knew that it had pretty good redox properties. And same goes for the ferrocene. It also has very good redox properties. So we were hoping that the cyclic voltammogram would look good like this. And so now that we had seen that our dyes perform pretty well electrochemically, so they could be oxidized and reduced without degrading to a large extent, we realized it's time to put these in a dye-sensitized solar cell and test their efficiency. Now, fabricating the dye-sensitized solar cells was such a process. It takes 2 to 3 days for every batch, and you do about 10 per batch. And it took a lot of effort. The first step is, of course, preparing the anodes and the cathodes. So we had to coat them with titanium dioxide nanoparticles. These helped the dye molecules actually stick to the anode, and that was our next step. And then we had to introduce an electrolyte solution. The electrolyte is critical. It helps return the electrons to the dye. And then we sealed the whole thing with the cathode. And now we were ready to test our dye-sensitized solar cells. Testing is really cool because we use a solar simulator. The solar simulator is meant to simulate the wavelengths of light that the sun would release. And so this solar simulator light is incredibly bright. And what we do is we shine that light on the dye-sensitized solar cell, and we measure how much of that light gets converted to electrical energy. Now, these calculations are quite complex, and there's lots of numbers involved. But looking at this table, the most important number is the solar cell efficiency, which is what we calculated. Really, these findings were incredibly disappointing. I mean, we thought that these dye molecules were going to be better than any molecules we'd ever had. We thought they were going to improve the efficiency. And what we actually saw is that the efficiency decreased when we added these ferrocene groups. But that's okay. In science, a lot of the times, your experiments will fail, or you will not get the results that you were hoping for. And that's a part of science, and it's an important part of science because you can help explain to others and teach others what not to do. You can help explain what went wrong. And really, that's what we decided to do. We said, okay, this is not working. These dye-sensitized solar cells sucked. But why did they suck? What went wrong in our experimental design? And so we had to go back to the drawing board. And we realized that we had another technique we could use called spectroelectrochemistry. Now, this technique is really interesting because what we do is we measure the dye's ability to absorb light while applying a voltage to the dye solution. Now, this helped give us visibility into what was happening to the dye when it was in a dye-sensitized solar cell. But we had a hunch that the dye and the electrolyte were interacting and something was going on. So we decided to add the electrolyte into our dye solution and apply a voltage to both the electrolyte and the dye. And we noticed that different things were happening to the absorption spectrum once we added the electrolyte. And that implied to us that the electrolyte was part of the problem. And it was potentially negatively interacting with the dye and affecting its ability to convert sunlight into electricity. And that's where we ended the paper. We didn't know exactly what went wrong, but we had evidence to support a theory where the electrolyte and the ferrocene in the dye were interacting negatively. And that was enough insight in order to get this paper published. We didn't get perfect results. We didn't make the best dye-sensitized solar cells, but we were able to learn something and share what we learned. And that's a critical part of science communication. We can't only communicate the wins, the good results. We have to communicate the losses, the bad results, because they help other researchers not make the same mistakes. They help other researchers learn what doesn't work. And that's almost as important as what does work. And so that's the end of this paper, and that's the end of my walkthrough of all my research. Anyways, thanks for listening. I hope you have a really nice day, and I'll see you in my next video.